Hi, everybody. Welcome back. Thanks for the lovely set of talks this morning. We've got a couple more talks now, as Roberto said, and then an update from all of our poster presenters. So for those of you who don't know me, I'm Ryan Hickox from Dartmouth College here in New Hampshire. We have nice snow outside, so it's different from Chile right now. Anyway, so what we're going to do is go through this set of talks. The first couple, again, will be 8 minutes plus 2 minutes for questions. And then we'll do the 1 minute poster talks, and then we'll have a discussion about a lot of the topics that we've discussed today. And so I'll have a few things to raise with that, but that'll mostly be, up to the audience to contribute to that discussion. Okay, so without further ado, our first talk in this third part of the session today is by Marie Lau from University of California, Riverside, and I will have her take it away.
Yeah, hi, I'm Marie Lau. Can you hear me? Hello, can people hear me? Yes.
Absolutely.
Thanks. I'm postdoc at UC Riverside. I'm presenting to you a work to be submitted soon. I'll begin with introducing why you should care about extremely red quasars. Then I'll describe our KCWI observations of the Lyman alpha halo around the reddest ELQ. Then I'll talk about what we infer about the circumgalactic medium and the illumination geometry of this ELQ and put it in the context of galaxy evolution. Next slide, the figure shows 3 intermediate stages in popular evolution models. Models predict that supermassive black holes initially grow in obscurity deep inside dusty galactic starbursts. The supermassive black holes grow until they are massive enough to power quasars. Outflows from the quasars then drive blowouts of gas and dust, which quench star formation. Then the blowouts reveal visibly luminous quasars in the galactic nuclei. Dust-obscured quasars are the middle stage here. They provide important tests of evolution models because they're expected to be young and powerful objects. They should appear during that brief transition phase of blowout. Many dusty quasar populations require more powerful physical properties than what could be just orientation effects. Dusty quasars are also the dominant population of the first quasars. The Hammond et al. Team discovered a population of dusty quasars that they named the extremely red quasars. ELQs are selected from the BOSS survey matched to WISE data. They're selected based on extremely red color from rest UV to the mid-infrared. ELQs are at redshifts 2 to 4 and have high bolometric luminosities greater than 10 to the 47 ergs per second. ELQs have the broadest and most blue-shifted O3 emission ever reported. The O3 outflows can carry speeds reaching 6,000 kilometers per second. Adaptive optics observations show that the O3 outflows happen on 1 kpc scales. To explore whether the outflows impact on the larger circumgalactic scales, we need wide-field integral field spectroscopy. Our team is building a KCWI sample of ELQs. The pilot study is on the reddest ELQ. I chose this J666 plus 1215 for KCWI observations, as is the reddest ELQ. The on-source time was 17 minutes. The figure on the left shows a spectrum extracted from a 1 arcsecond aperture centered on a quasar. I call it the core spectrum. It has a narrow emission line at Lyman alpha, which was already noted in the BOSS spectrum of this ELQ. The origin of this spike is speculated to be gas on larger scales than the quasar broadline region. And I used this Lyman alpha spike to define the systemic redshift. A note about modeling the quasar point spread function. The broadline region is partially obscured, so the narrow lines can be identified as distinct components. So to make a pure quasar spectrum from this core spectrum, I clip the Lyman alpha spike and the corresponding narrow emissions in carbon-4 and helium-2. So I subtract the quasar point spread function, and then I optimally extract the extended emissions. The figure on the right shows the extended Lyman alpha emission. The plus symbol marks the position of the quasar. Carbon-4 emission is detected in the inner halo, which means the inner halo is enriched with past outflows. Helium-2 emission is also detected in the inner halo. I quantify the asymmetry of this Lyman alpha halo, and I find that the inner halo on scales less than 30 kpc appears circularly symmetric, and the outer halo appears filamentary. For the inner halo, I calculate the line flux ratios. I find the helium-2 to Lyman alpha ratio is rather low. I create the Lyman alpha velocity centroid map. Majority of the Lyman alpha emission have small velocity shifts relative to the systemic. The velocity field is quiet down to the innermost region. The velocity field is coherent in the inner halo and shows some shear from the northern edge to the southern edge. Together with the filamentary morphology, I think the northern and southern edges trace inflowing streams. I define 3 apertures according to features on the velocity centroid map. I delineate an inner halo region, a southern outer halo region, and a northern outer halo region. The extracted aperture spectra are shown in a figure. I overplot the 1 arcsecond core aperture spectrum on this figure. The Lyman alpha spike in the core spectrum has a line profile very similar to the inner halo emission. This confirms that the spike in the Bose quasar spectrum originates from the inner halo. Both the core spectrum and the inner halo spectrum have a blue shifted absorption feature, which I think traces a moderate speed outflow. I compared the J666 line emitting halo with literature sources. These literature sources are Lyman alpha halos powered by type 1 and type 2 quasars, and they are matched in bolometric luminosity and cosmic redshift. Here I show a figure that compares the Lyman alpha nebular luminosities. The individual literature sources are plotted with small symbols, and the averages of the samples are plotted with larger symbols. The J666 measurement is within the wide and diverse range of other quasars. The nebular luminosity, nebula size, and kinematics are not exceptional, and there are marginal differences in the surface brightness radial profiles and asymmetry levels. The J666 halo is overall similarly asymmetric as other type 1 halos and is less asymmetric than type 2 halos. And the J666 helium-2 to Lyman alpha ratio in the inner halo is similarly low as other type 1 sources and is lower than type 2 sources. Here are some implications from the analysis results on J666. The J666 Lyman alpha halo is not dissimilar to other quasar-powered halos. There is not much evolution in the halo emission across quasar colors. The fast outflows driven by the ELQ happen within galactic scales. So the J666 Lyman alpha halo is kinematically quiet despite very fast O3 outflows. At present, no selection criteria on quasar properties systematically find fast outflows on circumgalactic scales. The Lyman alpha spike in the 1 arcsecond core spectrum of J666 arises from the inner halo. In general, narrow emission lines are good indicators of systemic redshifts. We find that halo emission properties transition near a distance of 30 kpc from the center. The inner halo is dominated by moderate speed outflows and past outflows, and the outer halo is dominated by inflows. A fundamental question about the nature of ELQs is whether the obscuration is due to orientation effects or a global dust distribution. Orientation effects may be caused by a dusty torus and axisymmetric ionization cones. On the other hand, a more global dust distribution may relate to more dusty and younger host galaxies. I'll argue that dust distribution in J666 is global and patchy. An obvious clue is the type 1 emission line properties of the quasar despite the extremely red color. Another clue is that the helium-2 to Lyman alpha ratio of the inner halo is as low as that of type 1 sources and is lower than type 2 sources. So the line of sight obscuration is patchy. Yet another clue is that the overall morphology of the Lyman alpha halo is less asymmetric than type 2 halos. Due to different orientations of the ionization cones, type 2 halos should appear more asymmetric than type 1 halos. I'll leave you with a summary slide. You may ask me for the literature data I compiled so you don't have to repeat the effort. Thank you.
Thank you very much, Marie. We have time for at least one question. Our first question is from Bojana Cherny, who asks, your outflow velocities are much smaller than BAL velocities. And so is the outflow mechanism different?
Oh, thank you for this question. So I think BAL velocities have a range of velocities, and yeah, I've seen BAL velocities that's higher than the O3 velocities here, and I've seen BAL velocities lower than the O3 velocities here. So if you only consider O3, I think ERQ's extremely red quasars have the fastest ever O3 outflow velocities ever reported, reaching 6,000 kilometers per second. And because of the atomic physics, O3 lines trace emission on KPC scales. And I think sometimes people try to measure or estimate the distance between the BAL system and a quasar, and it could be much less than that. And so I think it's not only the ionization state is different, but most importantly, O3 is tracing KPC scale outflows. So we know the outflows are impacting on the host galaxy and is causing what we call feedback.
Great, thank you very much. I think we need to move on to the next talk. So, but there is another question in the chat that we will post on Slack. So please continue the discussion there. And thank you very much again for a really interesting talk. Right. Our next talk is by Loli Martínez-Aldama, who's going to talk about Super-Eddington AGN. Take it away.
I think you're muted.
Couldn't see that. Yeah, Mary, you might be muted.
Now?
Yes.
Now it's okay? Okay,
Yep.
sorry.
No problem.
Okay. So my name is Loli Martínez-Aldama, and today I'm going to talk about our project with Super-Eddington AGNs and some of their applications. We can identify the Super-Eddington AGNs throughout the spectroscopic information. They used to show a strong low ionization lines with a kind of Lorentzian-like profiles. The oxygen 3 forbidden line is not really so strong in these sources, but they will show a strong contribution of the Fe2 in the optical and Fe3 in the UV. In the high ionization lines like carbon-4 or silicon-4, they will show blue asymmetries, which are an indication of outflows, and also we can have an idea of the radiation forces in this kind of objects. And also we can now detect a strong emission of the UV. In the photometric data, we can, these sources are really not so variable. The continuum variability is around less than 10%. And also they intend to show the really bluer color. So there is here, I'm showing an anti-correlation between the amplitude of variability and also the Eddington ratio. Most of these properties we know throughout the eigenvector 1, which is a scheme that organizes the spectral properties of GAGN. If we take the intensity of the Fe2 weighted by the H beta that is expressed by the parameter RFE, and we correlate with the width of H beta that basically gives us the information about the virial estimator, we will get that the AGNs are very well constrained in this region. We cannot observe AGNs in this region. So According to the spectroscopical fixtures, we can identify the Super-Eddington AGNs here. However, not only the spectral properties are well organized. We have identified using small samples that black hole mass, ionization parameter, and density apparently are also very well organized, and the driver suggests that it is the Eddington radio. It's very important to identify the role of the Eddington radio, and especially how is the behavior of this kind of sources, because it can change some of the standard scenarios that we have at AGN. The best example is for the radius luminosity relation. This relation is very popular because if we can estimate the size of the VLR, so then we can estimate the black hole mass. And it is most of the most famous relations used with this objective. However, some years ago, one group was devoted to analyze the Super-Eddington AGNs in the context of reverberation mapping. And they found that the Super-Eddington AGNs show a departure with respect to the standard radius luminosity relation. And apparently this departure was driven by the Eddington radio or a similar expression. So it's very important to apply a correction, because if not, we probably are getting a bad measurement of the black hole masses, especially if these sources are accreting close to the Eddington limit. A correction was proposed used the RFE parameter, the intensity of the FE2, because it is very well related with the Eddington radio. So now Du and Wan proposed this correction, including this parameter. So now we can say that we are in a very good stage with this. So that's why it's very important to analyze this object. If we observe the typical AGN spectra for the composite, we can get that in the 19,000 blend, that this is the one, this is the UV range, we will see that this peak is dominated by the carbon tree. However, when we observe that the accretion rate increase, we will see that the carbon tree is tiny, and other components like aluminum, silicon, and iron tree are taking more relevance. This is the typical, the blended spectrum that we observed in this kind of objects. Here you can see how the aluminum and also silicon tree are really very important, and carbon tree, it's not really important, but also here we have the high ionization line. So it's indicating that there are a different behavior between this object and the classical AGNs. So since the aluminum is very strong in this kind of objects, we are proposing to use the aluminum as a virial estimator. We know that we can observe magnesium-2 is the classical virial estimator in the UV. However, for high redshift sources, we can now observe with mostly of the instruments that we have this line. So we are proposed to use the aluminum because we can cover, or we can get this information around redshift 3 or larger. So we compare the information for the H beta line with the width of the aluminum, and we get basically a relation that is consistent with the 111. So why not to try to explore this kind of line with this objective? We also have found that these sources are associated with high metallicities. This is the carbon 4 profile. And if we blend the component in the profile in the virial component plus the outflow, that is the blue one, we can, using this flux radius and the photoionization model cloudy, we can get how is the metallicity of the gas. So we have found that for the virial component, the metallicity, ionization parameter, and density are really very well constrained in this region. But also we found that in these sources, there is a denser broadline region than in the typical AGNs. You see here the values are around 10 to 13. And also the metallicities are quite high. However, if we observe the behavior of the virial component, of the of the outflow, we will see that are really very spread. So we are proposing based on some features about the radio, but it have to be need more analysis, that probably this enhancement or this metal enrichment is by a resonance starburst in this kind of sources. It has been tested for sources around redshift 2.5, but we can do it for larger redshift sources. So for this project, I am proposing to use the SDSS reverberation mapping. this sample is continually monitoring, so we can observe how the broad components change and also the continuum. But in the case of the Super-Eddington AGN, since they are not super variable, we can get an average spectrum and of course increase the signal to noise that for a very good fitting. So aluminum is observed in this redshift range. So that's why I'm again proposing to use use this line with that object. It has a virial estimator. The previous fit were performed in one of the SDSS catalog. However, in this paper, they are now including one of the most important component, the Fe3 UV, that as I told you, here is this component is really important, but the multiplet in this, the UV34 multiplet here is really important. So usually in the classical AGNs, it's important the carbon 3, but in this case is the Fe2 plus a tiny carbon 3. So that's why we repeat the measurements using again automatic code. And these are our preliminary results. Our sample, the SDSS sample, is the blue stars. And here I'm comparing with other kind of Super-Eddington AGNs based on the accretion rate that these people is reporting. So you will see that really we are not in a crazy regimes of black hole masses. But the most interesting plot is when we plot the fundamental plane of the black hole mass and luminosity. Our sample is this one. For our sample, unfortunately, we are now getting really high Super-Eddington sources. The maximum value is around 0.6. And if I include the other sources, you will see that here really they appear to be to show a high Eddington radius, but really not so close, like equally to 1. So one of the applications that we really to use the Super-Eddington AGNs is with cosmology. Since these sources are radiating close to the Eddington limit, so we would suppose that this limit is 1, and we get that the radio black hole mass luminosity is constant, and we can get that the luminosity is proportional to the width of the line to the 4. So if we take this one, we can estimate, for example, distance independent of redshift. However, if we take only the sources larger than 3 that are the ones that satisfy more or less this condition that a lower limit, we will get this one. So unfortunately, we are not getting sources larger than 3 that was of the objective to use this kind of samples. So I know that in the literature, there are more objects that are really not analyzing the aluminum 3. So I invite to the community to publish the information of the aluminum 3, because in that case we can use and of course cover this region with and then make some estimation of cosmology with quasars. So this is my slide, and I am repeating this analysis using this new sample, the data from the SDSS5, and that's all. Thank you.
Thank you very much. Give everyone a second to put something in the questions. While we're waiting, I have one quick question, which is, do you have a sense of why carbon-4 estimates tend to go higher up in Eddington ratio? Do you think that that's a bias with the methods used to measure carbon-4, or is there something in particular about these ones that have been targeted with aluminum that tend to shy away from those highest Eddington sources?
Well, so we really, if I understand correctly, we really expect this kind of profiles because here the radiation forces are so strong. So it means that there is the accretion rate is making, since it is high, the radiation forces are taking more relevant, and that's why the gas in the carbon-4, that also is one of the gases very close to the continuum source, is given all this kind of energy. In fact, there are some low ionization lines in the H-beta, and in the H-beta particularly, if the Eddington radio is really high, we can observe also a hint of outflow. So it depends on the accretion rate, I guess, and radiation forces.
Great, thanks very much. Oh, okay, so let's we'll carry on. Thank you very much again, Mary, for this really interesting talk, and we'll carry on that discussion as well in the Slack channel. And now we're going to move on to our lightning round of poster talks. So each person, somebody has the posters on a shared screen, right?
Hi.
Hi.
Just a second.
No problem.
Here.
So to keep this to time, I know we got to keep you honest on these. So if anybody, once you get to about 5 seconds left, I'm going to start waving like crazy on this thing. And then when you actually get to 1 minute, I'll actually turn on my mic and then ask you to move along to the next person. So everybody, please try to keep your update to 1 minute, and hopefully we'll have a lot more discussion for these posters in the discussion later on. And so, once you're done, you can just introduce yourselves rather than having me introduce each person. So, Joao, if you're ready, let's take it away.
Okay. Can you see it?
Yes.
Can you see my screen?
Yep,
Yes, we can. So, hi everyone, my name is João Pedro. I'm from the Federal University of Rio Grande do Sul in Brazil, and I'm studying the galaxy NGC 6868 with GMOS IFU data. So I have performed stellar population synthesis and analyzed the ionized gas kinematics and fluxes. And basically what we see is a normal stellar population for these early type galaxies, so really old and high metallicity. And we also found a significant amount of dust in its center. And we also report a ionized gas disk, which was not previously found. This is an important study because of the high spatial resolution that we are able to achieve due to the small field of view of the GMOS instrument and the proximity of this galaxy at only 40 megaparsecs. So if you want to know more or have any questions about the details on the methods and other findings, please go to my poster and I will be happy to answer any questions you have. Thank you.
Okay, thank you very much.
Hi, everyone. My name is Brandon Castillo. I am a graduate student at Washington State University. My advisor is Vivian Baldessari, and we use the Kepler Space Telescope to search for and discover AGN. We use the Kepler Space Telescope because it has increased limits over ground-based telescopes and is uniquely designed to detect variability, which, as we know, is important to identify AGN. So we searched through 105 galaxies with the Hyperlita Galactic database and found 66 that were observed by Kepler. Using a custom pipeline, we created normalized light curves using custom aperture masks for each of these 66 galaxies, taking advantage of co-trending basis vectors to remove systematic noise inherent in Kepler data. To quantify variability, we used fractional variance. 3 objects with fractional variance above 2 times our standard deviations were found. 1 object light curve had inconclusive data shown in figure 3. So we believe we found 2 new AGN, one of which, the bottom one in figure 4, is a known X-ray source according to the NASA extragalactic database.
Great, thank you.
Hello, I'm Jack Delaney, and I'm from the University of Edinburgh. My supervisor is Dr. James Aird, and I'm presenting the extragalactic serendipitous swift survey XS and the constraints on the sky density and growth of supermassive black holes. So what is XS? XS is a extragalactic serendipitous survey created from the 2SXPS survey performed by the Swift X-ray telescope, and figure 1 shows how the coverage of those two vary, with XS in purple and 2SXPS in cyan. The XS sample consists of 3 bands, the medium, hard and total, covering the 1 to 2, 2 to 10 and 0.3 to 10 kV bands, with figure 2 showing the number of unique sources in a Venn diagram. Figure 3 is looking at the log n log s of the XS sample and comparing it to New Start and Swift BAT surveys, and overall we get a good agreement between these. And figure 4 shows how the XS sample the excess flux as a function of area and how it compares to other well-known surveys, including eROSITA. Thank you.
Thank you very much.
Hello, everybody. My name is Anastasio Díaz-Sánchez from the Universidad Politécnica de Cartagena in Spain. In this poster, I'm presenting the Molten Ring. The Molten Ring is an galaxy spiral length galaxy, redshift 1.48. This is a submillimeter galaxy. We have observed this with APES. And this galaxy has also a strong radio flux. In the radio regime, we can see an expressor break similar to the other submillimeter galaxy with AGNs. We have also historic data. We have reconstruct this source plane with our precise lensing model, and we have found two jet X-ray jets near to radio loads. For this result, we hope that this is a spiral galaxy with a supermassive black hole in the cosmos. Thank you very much.
Wonderful. Thank you very much.
Hi, everyone. My name is Marta. I'm a PhD student working with Jacqueline Hodge at Leiden University. So in the canonical model of massive galaxy evolution, unobscure quasars are the last evolutionary stage of high redshift dusty SMGs that have gas that has been depleted due to star formation AGN feedback. And star formation in these systems is thought to be residual and lasts for about a mega year. This has recently been brought into question by studies that have found several gas-rich unobscure quasars at intermediate redshifts. And to address this, I'm presenting here a program where we have targeted the CO2 to 1 line in a sample of 10 lens quasars at redshifts between 1 and 1.5 with NOEMA. We detect molecular gas in 70% of the targets and we find that they have enough co-molecular gas to sustain star formation for about 200 million years. A depletion time that's comparable to normal SMGs. And which is 2 orders of magnitude higher than what was expected. So if you would like to know more, please go check my poster or get in contact with me. Thank you.
Wonderful. Thank you very much.
Okay, so hello everyone. This is Ho from NLJ in Japan. And in this poster, we summarized our current study of 3 optically faint radio galaxies at redshift 3, which are selected from the Wilkes catalog. So Wilkes project searches for the optical counterparts of first radio sources of the super-low HSC images. And here, thanks to the deep and wide HSC imaging, we can find a new group of radio galaxies with optically faint but high radio loudness feature. And we carried out spectroscopic follow-up observations with QGACT arrays and identified 3 among them to be at redshift 3. Based on their spectrum, we found those hazy radio galaxies are likely to reset in gas-rich environment, and they might be at early stage of interactions between AGN radio jet and the host galaxy. So if you're interested in this study, please go to see my poster. Thank you.
Thank you very much.
Hello, everyone. I'm Alexander Messick, a graduate student at Washington State University, working with Vivian Baldessari, and we're presenting an X-ray analysis of 15 low-mass galaxies selected for their optical variability in Baldessari 2020. These include 9 new and 6 archival observations from the Chandra Observatory. 7 of our 15 galaxies in our sample yielded detections in the broadband with luminosities ranging from 6 times 10 to the 37 to 9 times 10 to the 42 ergs per second. We then compared these luminosities against the expected luminosity contribution from X-ray binaries, resulting in 5 of our 7 detected galaxies having luminosities higher than this contribution. We also conducted emission line diagnostics when possible with a BPT diagram, which categorized 2 of our objects as AGN, 6 as being dominated by star formation, and 2 as falling in the composite region. These discrepancies in AGN detection highlight possible biases in our current methods, particularly undercounting low mass and low metallicity systems, warranting further investigation.
All right, thank you very much.
Hi everyone, I'm Stephen Molyneux. I'm a 3rd-year PhD student currently at the European Sun Observatory, where I'm studying the role of molecular gas in quasar feedback. So this work is being done as part of the Quasar Feedback Survey, which is a multi-wavelength survey of 42 quasars at redshift less than 0.2. As part of that, I'm studying 17 of these targets, looking at the first 3 transitions of CO and making comparisons to in-hand observations of the ionized gas and the radio emission. So in particular, we're looking at the line profiles and evidence of outflows, like in the spectrum on the left. And we're also interested in the excitation of the gas as well. and making comparisons to the radio emission and the ionized gas. And we are seeing tentative signs that there could be differences in the excitation based on different properties of the radio emission and the ionized gas. So yeah, if you want to check out more, please have a look at the poster and feel free to contact me on Slack or by email. Thank you.
Thank you very much.
Hi, I'm Atush back. And in my poster, I'm addressing one really underexplored dimension of higher-redshift galaxies, which is their dense gas content. So we conducted the largest survey of HCN 120, which should trace dense gas in higher-redshift galaxies. And we wanted to test the hypothesis whether they contain large amounts of dense gas. Turns out they don't. They seem to have less dense gas than would expect based on the star formation rate. They seem to have relatively low dense gas fractions and elevated star forming efficiency. And this might modify the way how we look at these galaxies and also inform future zoom-in simulations. Thank you.
All right, thank you very much.
Hi, everyone. I'm Grisha Zeltin, a PhD student from Tel Aviv University, and I'm going to briefly present a new paper where we calculated the contribution of AGN accretion disks to hydrogen reionization. We approached this question by calculating how the evolving BH parameters affect the emergent ionizing SED for various growth scenarios for the earliest supermassive black hole population, including super-Eddington accretion. And our findings suggest that accounting for the spectral evolution of accretion disks can increase the ionizing output by up to 80%. But that the contribution to reionization of AGNs is likely subdominant to the one of galaxies and can be probably significant only at low redshifts. The contribution can be, however, extended in principle to higher redshifts by a slower mass evolution, meaning a low accretion rate and or high spin. And lastly, our calculations can also reproduce the sizes of the proximity zones observed around high redshift quasars. And if you're interested, please see the poster and the paper and feel free to contact me for more details.
Thank you very much. Okay, thank you very much to all of the poster presenters. You will see on the Slack channel that the posters are all up there, and I encourage anyone with questions for those with the posters to please communicate with them over the Slack channel or in whatever other method you would like. But it's great you can get PDFs of them and see how their contributions to this discussion. Okay, so now we have about half an hour for a discussion among the group here, and I have a few prepared a few slides here to kind of get at some themes that we have discussed so far. There we go. Okay, so really, and I have also a few questions for the audience that I would like to pose you using a little bit of polling software. Anybody who's been at one of the conferences that I've organized with my colleagues at Durham University know we love asking questions of the audience. But I think the first question, which was really driven by, at least to me, driven by some of the first talks in the session, really is how does star formation in the early universe proceed? We have these wonderful new constraints using ALMA in particular to trace out the molecular gas and trace out the other, we can also probe atomic gas and other constituencies of that form the galaxies and actually try to look at in detail now, especially with ALMA, we can resolve individual galaxies and see how much gas is coming in, how much is going out, how much is forming stars, and what the evolution of these structures really would look like. And by the way, what I've done in each one of these slides as I go through here, I've highlighted a figure from one of the posters. I didn't have time as the talks were going by. I didn't trust myself to capture a screenshot appropriately from the talks, but the posters were up there. So I've put these together, and I also just want to again highlight the work done by those who have presented the posters. And so at least the way I sort of took away a lot of this discussion was that there are several components that matter. Molecular gas, atomic gas, we can see ionized gas. These can be seen in both inflow and outflow. And also the galaxy potential, which you can think of as both being the structure of the galaxy, but also what happens with mergers and interactions, all seem to drive the amount of gas that's getting into this molecular phase and the amount of stars that are forming, and also the way that the feedback proceeds. So the fitting all those together is obviously is a complex picture, but maybe it's something that we can discuss. The second thing that I noticed that came up multiple times in the session was the fact that in powerful star-forming galaxies at high redshift, there may be fast gas depletion, that some of these things may actually have low gas fractions or very rapid gas depletion times. And so Rodrigo is on here. I asked him the question about how long it would take for a galaxy to become passive. And I think that question is this really what we're seeing, that these rapid star forming systems that we see in the early universe are actually sort of rapidly burning through their gas? I think that's a really interesting question. So I kind of want to start the discussion there. I do have a question for the group, but it's a little bit more technical. So if anybody has something that they would like to sort of contribute at this point, please raise your hand or throw something in the chat. Okay, I'm gonna hopefully have a controversial point here to make the discussion a little bit better. So as we go forward, here's my question. So I'm going to ask the audience about this. What you can do, hopefully this will work for everyone. If you go to this website at the top, polev.com/blackhole, you should have an option to select one of these questions. One thing that came up to me a lot in this first in the talks today was that there's a lot of discussion about gas masses, about dust masses, about dust temperatures, and also star formation rates. And they use different combinations of different tracers, like for example C2 or continuum emission or whatever, in order to be able to measure these things. Now, is anybody trying this and it's not working? Because I'm not seeing. Can you paste the link? Oh yes,
Ryan, do you have to log in? Do you have to have an account to?
I don't. I said it so that you didn't, but is it making you? Is it saying that you need to be registered?
At least in my case, but maybe.
To register, you hit Google a few times and you get there. At least that was my experience.
Okay,
I'll
sorry about that. It does that sometimes, but I deliberately. No, it's here.
I didn't have to register. I went through.
Okay, yes, and we have a result. We have one in. Excellent. But we have 126 people on the call, so hopefully we'll get more in a minute here. And honestly, I think what I'd like to hear, especially from the experts or some people in the audience, maybe you haven't discussed this, is how well we really feel like we understand this, because we have all these different measures for how much dust mass we have, what the star formation rate is, but these are all connected to each other in ways that are not totally trivial. And I must admit, as somebody who works more on AGN, I'm never completely sure how strongly these are degenerate with each other, yet they're really important when we're trying to understand what's going on in these galaxies at high redshift. So I'll wait another minute or two, or 30 seconds to see if any more results come in. Here. It should, and someone was asking, just a second. Go back. Oh, yes, Michael.
Would you? I don't know if you want people to just jump in and say things.
I think. Well, let me show the results here really quick. We have almost enough, and then so once we see the responses, yes, then I'd like people to jump in. Here we go. Okay. So, I love questions like this. This is why we have conferences. Wonderful. But I love that nobody has said A here. Which means we have a lot to do. So Michael, yes, please. What do you?
I was one of those who clicked D, still uncertain due to uncertainties.
What I meant was measurement uncertainties. I'm sorry.
No, but I interpreted it literally because I think there are sort of fundamental uncertainties in what exactly we're measuring. there's all these parameters we throw around, like dust to gas ratios and metallicities and temperatures that are all coupled questions extrapolated from low redshift experience in a variety of ways that we sort of cross our fingers, calibrate with larger or smaller error bars to some extent, and pray that they're pretty good. But I think that falls under the category of still uncertain due to uncertainties, which is why I clicked that. That's my provocative response to you.
Great. Laura.
Yeah, sorry about what was just said. It's true that in some cases, especially when we have one data point, as I was showing in the case of our method, we have to rely on dust to gas ratios and metallicities and so on and so forth. But it's also true that, for instance, we recently have been observing also high redshift galaxies in ALMA band 9. This was presented, for instance, in a paper that we have been writing with Tom Bax. And this was the first ever scaling the peak of the infrared SD peak at the shorter wavelength side. And in this case, we could really constrain the dust temperature and the dust mass to an unprecedented precision. Yes, we still have to rely on some modeling for the mid-infrared because there's no observation there. And surely we maybe have to assume a dust emissivity index and so on and so forth, but that is true also for some low redshift stuff. So I would say that we are still making progress, despite I also put the still uncertainty to observational errors.
Great, Rodrigo.
Yeah, no, I agree with Laura. I think at least what I tried to show in my talk, but I don't know if maybe I forgot to mention, is that one of the nice conclusions of the review written by Linda Tacconi is that if you look at the molecular gas base, the molecular gases based on the CO and the dust, which is mostly coming from the work by Nick Scoville, you do find a good agreement between both methods up to redshift 2. So I would say, how well do we understand these gas masses? Up to redshift 2 probably is looking very promising. Beyond that, of course, it's more complicated. But at least we're at a point where we can break by redshift and to say, okay, at least in this redshift range, different methods, agree. And then, yeah, the other is the unexplored territory that Laura and others, we're trying to understand and constrain better.
Great. Just a second. Marianne, you had a question or a comment?
No, I was just trying to figure out how you.
Okay. If anybody does, we can. If you raise your hand, we can unmute anybody on the in the session right now. So you're welcome.
Well, thank you. I'm sorry.
No worries.
Yeah.
Okay. I just want to raise this as a point of discussion. Hopefully, a lot of this will then be able to, our thoughts about how effectively we can do this and what this really means for galaxy formation can carry along later on in the meeting. I think the next question, which was raised several times in talks this morning, this is something I find super interesting, is what really is the full population of growing black holes in galaxies? And a lot of this was covered by some work in the posters as well. And so we have a number of examples of ways in which we're making progress on this. One is, like Paulina mentioned in her talk, is variability. And this shows this lovely Kepler light curve that Brandon showed in his poster. We know that variability of AGN is a really is potentially can set them apart. And as Michael mentioned about the Rubin Observatory coming online, all of a sudden we're going to have this amazing data set that in principle could use that selection technique for a huge part of the sky. And so how we potentially will be able to uncover new AGN that way. There's also this question about low mass black holes and black holes in dwarf galaxies that are sort of filling in the lower mass end, and there may be constraints having to do with how the seeds form and all that stuff from that kind of work. And then there are also still large surveys, and Michael mentioned a couple of those, but there's also really good serendipitous work. We have eRosita now doing observations of the whole sky in the X-rays that will be able to potentially give us newer populations of especially the rare sources. And then finally, I just want to point toward, because there were a couple talks on this, the very highest redshift AGN. We're really kind of pushing in that direction, starting to move down the mass function and the luminosity function. But I'd like to second something that Michael mentioned, which is that even at this point, we're still not getting the bulk of the black holes and at those very high redshift. And one has to be very careful trying to wag the dog with the tail and actually understand what's going on of the whole population when you're necessarily flux limited and luminosity limited. So that brings me to my next question, and hopefully people have this working now, at least most of you do, which is, and this is not really like a factual question. I'm just curious what the audience thinks. Which is the most interesting missing black hole population, the ones that we haven't really just found that many of yet? Higher redshift, lower mass black holes of the type that that Michael was describing, intermediate mass black holes in dwarf galaxies, variability selected black holes, and Paulina made a good point in the chat that they won't tell you very much about obscured sources. Heavily obscured black holes, or half of us here are galaxy people, and black holes are really not all that interesting. I'll give a second here to get some responses from the group.
We can't click all of the above, unfortunately. Or
no,
A through D.
I actually did that with I gave a public talk and did that with a poll, and everybody told me it was a cop-out because everybody would just say, oh. So
they're all wonderful, right?
Like choosing between.
We love them.
Yeah. Anyway, all right. I'm surprised that nobody from Washington State here has said variability select black holes, because I know you guys are really excited about that. But again, this is a great one because it's all across the board, and this is showing. Here we go. Oh, great, excellent. This is showing us really how much parameter space we really have to measure. And Paula makes a good point that the most interesting black holes are the ones that we don't know anything about yet. And I think that may be true. So for example, at least in my, there is speculation that there may be wandering supermassive black holes out there that are produced during mergers, maybe early in the universe. And they'd be very hard to find. And actually, if you work out some things about the total AGN population and the total mass in black holes, it's actually possible that those things are a way to explain the fact that we see so many obscured AGN in high redshift. Anyway, I think that's one good example of ones we maybe would miss. So does anybody have any thoughts or comments on sort of where the field is going in trying to uncover all these different types of black holes?
I'll just give a shout out. I answered D, but again, I wanted to click everything. I think I mean, the intermediate mass black hole question is so key for us to try to understand what the how these black holes formed in the first place, and to what extent we can extrapolate what we currently know to the full quasar population. So I suspect that the most interesting new developments will be in category B in the next 5 or 10 years. Just so much exciting stuff happening there.
Great. Any other thoughts or comments on this topic?
There is one comment on the general chat, essentially, that by Paula Rodriguez, saying that the most interesting is the one we don't know anything about yet. And yet there is, yeah, that space for discovery with the future surveys and missions, right?
Absolutely. And I mean, we have entirely new windows, right? I mean, Lisa, for example, I mean, we opened up, turned on LIGO and found black holes that nobody had, well, I mean, some people had, but I think most people hadn't really been thinking a lot about 30 to 50 solar mass black holes before LIGO turned on. And yet they're all over the place, seems to be, or at least, they produce mergers that LIGO can detect. And likewise, it may very well be that once we have LISA, we find a population that we didn't even necessarily know, consider that strongly before. I would just point out, somebody made Marie made the point in the chat that high redshift black holes are heavily obscured, and indeed, that's absolutely true. And there does seem to be a evolution in the obscured fraction at some level. one thing we're finding, and this is to highlight, actually, I'm going to take my sitting in my chair here at Dartmouth, take one opportunity to highlight some of the work by people here, Chris Carroll, who's now a postdoc at Washington State, and Tanima Nana, who's a postdoc here at Dartmouth. Together, they've done some theoretical and some observational work that seems to suggest that heavily obscured, like Compton-thick AGN, are well more than half of the total population, which we've been kind of trending that way with a number of different observations, but I think some of their work has been really starting to get pretty definitive about the fact that there really are a lot of heavily obscured black holes out there. And indeed, some of them may be sitting in these dwarf galaxies. And so that's something that will combine these, I think, in a really interesting way. And JWST will uncover a lot of them with higher ionization lines. It's absolutely true. I think that's very exciting. Okay, one last topic. And this
Ryan,
is,
sorry, I think Vivian raised her hand.
Oh, Vivian, raise your hand. Oh, shoot. I didn't see it.
Someone unmuted me. Yeah, I just wanted to address the overlap between intermediate mass black holes and dwarf galaxies and variability selected objects, since a lot of us are really excited about both of those topics. And as Paulina said really nicely in her talk, many of these are missed through searches for broad lines or through narrow line ratios. And so variability turns out offers a really great opportunity to find a lot of these objects that we would otherwise miss. So I think many of us would have chosen B and C if we had had a multiple choice option.
Great. Thanks, Vivian. Okay, let's move on to what, and you'll see this is black hole focused, but you choose me for a moderator, that's what you get. My last one here is this big question that we've been talking about for many years now, but especially in the last 15 or 20 years, which is how do black holes impact their large scale environment? And by large scale environment, I'm meaning both, actually really should just say environment, in both their galaxies and also the areas outside them. And we saw a number of talks about this, about outflows and what happens with rapid accretion, what observing various kind of gas kinematics, et cetera. We also heard a little bit about inflows as well, and sort of potentially the dynamics between those. But I've just showed here some slides from some of the posters talking about the fact that quasar hosts maybe have a little bit less molecular gas than corresponding, for example, submillimeter galaxies. That some galaxies maybe are gas depleted in a way that would suggest black hole feedback, that radio jets seem to be able to produce impacts on black holes, and that we saw a couple of talks and also a poster about big Lyman alpha halos that can be produced by growing black holes, and can also produce proximity zones and ultimately in the early universe contribute to reionization. And so there are all these different ways and different scales and redshift at which black hole feedback is potentially important. But, and this is the but, we also know, and we heard from Rodrigo in the first talk, that star formation itself also produces a large impact on the systems that it lives in. You can drive, supernovae are not energetic things, right? And the radiation pressure can potentially be important. What happened? Oh, there we go. And so my question for you is, and this is kind of a leading question, but how important is black hole feedback on star formation in galaxies? Is it very? You can't explain any of the observations without it, or most of the observations without it. Sort of, and it really depends on the type of the system and the redshift. So black hole feedback can be important in subsystems at all, not at all. And we know there's feedback. So we'd be suggesting star formation feedback is definitely more important, or we still have absolutely no idea. And part of me is tempted to answer D on this, having worked on this problem for many years. But I think I think we're understanding that it must be important at some level. All right, let's see what people think. Right, we finally have consensus. And the consensus is that we don't know exactly, which is great. So I'm curious, does anybody have any thoughts on this? So Marie mentioned this is very interesting. Neil Brandt's talk, which I think is based on work by a number of graduate students, sort of, and postdocs in his group over a number of years, has shown that black hole growth depends little on cosmic environment beyond the size of the galaxy, 100 kiloparsecs or so. And I think that actually, I would say that a number of different results actually seem to suggest that that's true, that the feeding mechanism of black holes is probably not so important on what's happening on large scales. If you do clustering measurements, if you do environment measurements, once you average over the stochastic changes in the black hole accretion, that seems to be the result that you get. So maybe on large scale environments, there is not that much of a difference. But on smaller scales, potentially there still is an impact. And I'm curious if anybody has any thoughts on that. And also, you could, in principle, be producing proximity zones and large alignment alpha nebulae and everything on quite large scales without necessarily influencing the feeding. So should option B, we should mention the type of system, right, and the scales. I think that's a very good point, Laura. Thanks. So who wants to contribute? We have 4 minutes here to cover this entire field.
I just wanted to say that at least for the redshift 4 to 5 galaxies and the results that I showed today in the talk about star formation driven outflows, I mean, really with JWST we'll be able to actually do BPT diagrams of the central part of these galaxies and really know what is driving these outflows that we now detect. So I don't want to give the impression that I just said in my talk that this is all star formation driven outflows and this is the main source of feedback at this high redshift. It's just we don't know yet, but JWST will help a lot for sure.
Super. Kiara, allowed to talk. There we go.
Great. Hi everybody. Thank you for the discussion. And I hope we're having a bit more discussion on this on Thursday. But something that bugs my mind is also about the redshift part that you have in your reply B. And for instance, you have spinning like, do the environment, do the black hole do something on the environment around it? And then my question would also be, do the environment know there is a black hole there? Because for instance, at higher redshift, you think, oh, larger black holes should be living in very massive dark matter halos and surrounded by galaxies, but then you also see protoclusters of galaxies without apparent black hole signatures. So the other question there, I think, is also what's the other way around? And that really changes with redshift as well, and how the protoclusters or clusters of galaxies act on their evolution of the galaxies in them, depending on the redshift that we see. So yeah, I don't know if this is too much of a large question to ask at the very end of this discussion, but I think this is also interesting.
That's great. I think thank you, Kiara. I think that actually sort of opens up a whole set of questions as well. And it gets to one interesting question, which is sort of related, which is that we know the hot atmospheres of massive structures at low redshift must be influenced by the presence of a black hole. And there's plenty of really excellent work looking at X-ray atmospheres showing that, there are these scaling relationships and that there's clear, I mean, you see the cavities, that there must be some impact there. But not necessarily at high redshift. And it's an interesting question to ask, when do these structures really settle down to where you get, where this sort of feedback and so real feedback, right, self-regulation mechanism maybe actually kicks in. And, with deeper X-ray observations and other ways in which we can measure the ISM properties at high redshift and the ICM properties, then we may be able to start answering that. Christopher also mentions, and this is a really interesting point, and I think one that has really not been addressed that much, which is that the effect of on the ISM depends on the angle of the black hole disk with respect to the galaxy's disk. And I would completely agree with this. And this is one way in which there's been a lot of discussion over the last 20 years about whether having a bulge is important in terms of the efficiency of black hole feedback. And the advantage of a bulge is that it's basically quasi-spherical, right? Whereas the disk is dense along one particular direction. And that could really impact how effective black holes are at pushing against material outside. And so how much that affects disks, and are there intermittent periods where the black hole is pointed in the right direction and then will actually be affecting the disk, I think is a really interesting and somewhat open question. Okay, we are exactly at 1:30. And we could go on for hours and hours doing this, but I think what hopefully that we've done here a little bit is just seeded some of the discussion that we'll be doing later on. Roberto or other organizers, does anybody have any final word you'd like to mention or anything else to add for the day?
No, I don't think so. I think it's been a great day, fantastic talks, great discussion. So just to thank everybody, all of the speakers, all of the moderators, thank you very much. And yeah, there's no other information, so we can stop here and see you tomorrow.